Swayam Prabha. Digital India. Educated India.
Welcome to the third lecture on constitutive modeling of piezoelectric materials. So, in the last lecture, we talked about the first and second law of thermodynamics. So, today we will continue with that. Now, we will relate the first and second law and we will get some equation from where it becomes easier for us to derive the constitutive relations. So, combining first and second law of thermodynamics, we get T s dot plus sigma I j epsilon I j plus E d I minus u dot minus q I t multiplied by t greater than equal to 0. Now, u here is function of the strain, electric vector, electrical displacement and entropy S. Now, so these are the state variables here. So, if that is the case, then u dot should be is equal to del u by del epsilon I j divided by epsilon I j dot plus del u divided by del d I multiplied by d I dot plus del u by del s multiplied by s dot. So, if we put it here, this becomes sigma I j minus del u by del epsilon I j multiplied by epsilon I j dot plus E I minus del u by del d I into d I dot plus t minus del u by del s multiplied by s dot minus q I by t multiplied by t comma I greater than equal to 0. Now, it should hold for any process. So, this relation should hold for any process. So, it should hold for any, so which means that it should hold for any epsilon I j dot d I dot and s I dot. So, if that is the case, then the only possibility is sigma I j minus del u by is 0, which means that sigma I j is equal to del u by del epsilon ij, and then accordingly we get EI, electric field I is equal to del u by del I, and T is equal to del u by del S. Now we saw that this sigma as a matrix can be simplified as sigma as a vector, because we have already assumed that our stress matrix is symmetric by ignoring the moment due to electric field and polarization. So, if that is the case, then sigma can be assumed to be a vector, and accordingly epsilon ij can also be assumed to be a vector. So, if we do that, then we can write simply sigma I is equal to or maybe we can use a different index, maybe sigma m is equal to del u by del epsilon m, where m goes from 1 to 6, because it has both stress and strain has 6 components. So, we wrote our stress matrix as a vector by assuming that the shear stresses are, complementary shear stresses are same, and similarly the epsilon matrix, the strain matrix, can also assume to be a vector of 6 quantities, assuming that the complementary shear strains are equal, and that helps us write it in this way. Now, but again we will simplify the notations, and with that simplification of notation we can write increment in sigma, which is d sigma. So, we are not carrying out with any suffix ij or m, just for the simplification, and we can write this as del sigma by del epsilon, keeping d and s constant, multiplied by d epsilon, plus del sigma by del d, keeping epsilon and s constant, plus del sigma by del s, keeping d and epsilon as constant. Similarly, we can take the we have to multiply dd and ds here also, like what we did here. So, these are partial derivatives with respect to some state multiplied by d of that state and their summation. Accordingly, we can write T of electric field E. Again, electric field is a vector, but we have just simplified it and we are not carrying these suffixes. This keeping T and S constant multiplied by T E, plus this divided by D, keeping epsilon and S as constant, by S, keeping D and epsilon as constant, and accordingly we can write dt as delta T by delta epsilon, keeping D and S as constant, multiplied by d epsilon, plus delta T by delta D, epsilon and S as constant, multiplied by, again we have to multiply this dd and ds and dd and del s, keeping d and epsilon as constant, multiplied by ds. Now, this sigma has 6 components, so there can be 6 equations like that. So, this will give us a 6 by 6 matrix, and there will be 6 of these d epsilons, and there are 3 number of d's. So, this will give us a 6 by 3 system, and s is just one s, so it will give us a 6 by 1 system. Likewise, we will get things here. Now, what we do is we will simplify it further and we will assume a purely electromechanical process. So, considering only the electromechanical effect, if we consider only the electromechanical effect, these two quantities can be taken out and similarly this entire equation can be taken out. So, we are considered only the electrical and mechanical quantities. So, we do not incorporate temperature in our problem. So, we will make use of these equations after some time. Now, before that, now let us write increment of sigma as del epsilon, because we have seen that the first term here is del epsilon by del sigma multiplied by dE, del sigma by del epsilon multiplied by dE, and sigma is already del u by del epsilon. So, we can write this plus del to u by del epsilon del d multiplied by dd. So, the second term in the expression for d sigma was del sigma by del d, and again sigma is equal to del u by del epsilon. So, we can write this. Accordingly, we can write dE as del to u by del epsilon del d into d epsilon plus del to u by del d2 into dd. Now, this is sigma is a 6 by 1 vector and epsilon is a 6 by 1 vector. So, we will and d is a 3 by 1 vector. So, we are going to get 6 equations out of it and it is going to give me a 6 by 1 matrix, and similarly this is going to give me 6 by 3 matrix, this is going to give me 3 by 6 because E is 3 by 1 and epsilon is 6 by 1, and this is going to give me 3 by 3 matrix. So, with that we can write sigma epsilon is equal to CD and this is epsilon 6 by 1, this is our d 3 by 1 and this is also 6 by 1, this is 3 by 1. So, this is our one constitutive relation where epsilon and d, strain and displacement are my epsilon and displacement are my states. So, this is one form of the constitutive relations. Now, here I am writing CD. So, C relates strain, C relates stress with the strain, and we are putting this D superscript because the other state vector is D. Similarly, we are writing beta here. So, beta is relating electric field with the displacement, electrical displacement, and we are putting a superscript epsilon because the other state vector is epsilon. Now we will try to write the constitutive relation in a different form. So the internal energy in the differential form can be written as du is equal to sigma d epsilon plus E d d. Now we will define another thermodynamic potential enthalpy as H is equal to U minus E d. So if I take dH is equal to du, then it becomes electric field multiplied by dd minus d multiplied by differential of the electric field. So if I take this du here, finally the expression becomes sigma d epsilon minus d electric field E. Now we can write dH as also del of H divided by del of del H by del epsilon, keeping electric field as constant multiplied by d epsilon plus del H by del E, keeping epsilon as constant multiplied by dE. So from here we can say that del H by del E is our sigma. So if I relate this with this relation, then we can say that del H by del epsilon is sigma and del H by del E is minus of d. Now what we do is we write d sigma, increment in stress, so we write d sigma as del sigma by del epsilon, keeping E as constant multiplied by dE plus del sigma by del E, keeping epsilon as constant multiplied by d electric field, and that from that we can write this as del 2H by del epsilon 2 into dE plus del 2H into del E and multiplied by del E. Accordingly, we can write dd as d by d epsilon, keeping electric field as constant, multiplied by dE plus dD by dE, keeping epsilon as constant, multiplied by dE, and this we can again rewrite as, if we put d in terms of h, and then we can write as minus del to h plus dE. So, we have this, and again we can combining these two relations, we can write a constitutive relation in this form, which is C E E. So, these are again some new constants that we are defining. And this. So, this is a 6 by 1 vector, this is a 3 by 1 vector, this is 6 by 1 and this is 3 by 1. So, this is 6 by 6, this is 6 by 3, this is 3 by 6, this is 3 by 3. So, here we are using just if you look back, we are using two epsilons. One epsilon is for strain, and then there is another form of epsilon that is here, which is generally called a lunate epsilon, and that is here to denote this constant. So, two variations of epsilon we are using, one for strain and one for this electrical constant, and it is not a coupling constant, it is just relating this electrical variable electric field to D. So, here the C relates stress and strain, and this epsilon relates electrical displacement and electrical field, and here E is a coupling constant which relates stress with electric field and electrical displacement with strain. So, that is how the electrical and mechanical terms are coupled here, and it was similar in the previous constitutive equation that we derived too. So, there the coupling constant was D. Now, in that expression the coupling constant was H in the previous constitutive relation, and we will get more coupling constants like D, G as we move along and as we keep changing the state variables. So, initially we had internal energy as our thermodynamic potential, and from there we changed to enthalpy as our new potential. So, the stress one of the state variable was D in the internal energy, and then after we change it to a new potential enthalpy, then instead of electrical displacement D, our electric field E become the state vector. Now, that change of this potential through that transformation that we did is called Legendre transformation. So, we will do another Legendre transformation to get a new potential, and this potential is Helmholtz free energy. So, let us define this as F as internal energy minus stress multiplied by strain. So, in the differential form, this can be written as du minus d sigma minus epsilon d epsilon multiplied by sigma minus d sigma multiplied by epsilon, and then it becomes sigma d epsilon plus EDD minus sigma d epsilon minus epsilon d sigma, and finally the quantity is minus epsilon d sigma plus EDD. Now we can also write df as df del f by del sigma, keeping d as constant multiplied by d sigma plus del f by del d, keeping sigma as constant multiplied by dd. Now if I compare this with this, we can write del f by del sigma as minus of epsilon, and we can write del f by del d as electric field E. Now we can write the differential form of the strain del epsilon by del d, keeping d as constant multiplied by d sigma plus del epsilon, sorry, it should be sigma. So del epsilon by del sigma, keeping d as constant multiplied by d sigma, del epsilon by del d, keeping sigma as constant multiplied by dd. Now we know that epsilon is equal to minus of del f by del sigma. So with that we can write this and this. Similarly, we can define the differential form of the electric field, and that can be written as keeping d constant plus del d, keeping sigma constant. And again we know that E is equal to del f by del d. So this becomes del to f by del sigma del d plus del to f by del d2. Now if we combine these two, we can write one more constitutive relation, and that we can write in this form. So again it is 6 by 1 vector, and this is a 3 by 1 vector, this is 6 by 1 vector, and this is a 3 by 1 vector. So this is 6 by 6, this is 6 by 3, this is 3 by 6, and this is 3 by 3. So we got another constitutive relation where my state vectors are stress and electrical displacement D. So, with that we would conclude this lecture. So, there is one more form of the constitutive relations that we will see in the next lecture, and after that we will see the interrelation between the constants that we get from each of these constitutive relations. So, thank you.